Good afternoon. Welcome to Western Water Assessment's webinar on extreme heat in the West. My name is Seth Arens. I work as a research scientist for Western Water Assessment. I'm a physical and biological scientist and work with stakeholders in the Intermountain West and especially Utah to help foster a greater understanding of climate change, its impacts, and how to adapt to those changes. Today, I'm going to be introducing extreme heat and kind of a historical context of extreme heat within the Intermountain West, so Colorado, Wyoming, and Utah, and start to talk a little bit about how climate change is impacting extreme heat. Our discussion today will include two other speakers. The first of those is Nels Bjarke. He is a fourth-year PhD candidate at the University of Colorado Boulder in the Hydrology, Water Resources, and Environmental Fluid Mechanics group. Nels's research focuses on evaluating climate change impacts on surface water availability, multi-year droughts, and heat probabilities across the Western U.S. Nels will be presenting results from a project evaluating the historical likelihood of extreme heat waves observed in the West during the past couple of years, and talking more broadly about our general understanding of extreme heat probability now and in the future. Finishing our webinar will be Katie Clifford. Katie is a human geographer and Western Water Assessment's social science lead. She does engaged research in partnership with communities and managers on climate adaptation issues, including environmental justice, natural and compound hazards, and environmental management. Katie will be exploring some of the impacts and implications of extreme heat for communities and managers with a focus on equity issues. Throughout the talk, if any of in the audience here has questions, please type those into the Q&A tab at the bottom of your Zoom screen. At the very end of our webinar, we will answer questions as long as we have time for it within the hour. All right, so I'll be talking about giving an introduction to extreme heat in the West. Before we dive into some more detailed information about extreme heat, I'd like to go over some definitions of extreme heat. And one of the reasons why is because there's really no consistent definition of extreme heat. It can mean quite a few different definitions are used. One common definition are daily temperature records, or all-time temperature records at given sites. Another definition of extreme heat can be a temperature threshold, such as 100 degrees. In this case, maybe the number of days over 100 degrees in a given year. Also, heat waves are sometimes used as a definition of extreme heat. And for the purpose of this talk, I'll be defining heat waves as three or more consecutive days where temperatures are 100 degrees or greater. Another aspect of extreme heat that's a definition that's less commonly used, but especially important when thinking about human health, are nighttime temperature thresholds. I'll be giving information a little bit about when minimum temperatures are greater than 75 degrees. The heat index is also used as a definition of extreme heat and used as a threshold for defining extreme heat. And the heat index includes both temperature and relative humidity. We use this a bit less in the West because generally our relative humidities are very low. However, if you look at, say, extreme heat vulnerability across the United States, you'll often see very high levels of extreme heat vulnerability in the southeastern United States. And this is because they have relatively hot temperatures, maybe as high as the low hundreds, but also very high relative humidities. And then a final definition of extreme heat can be using probability as a definition. So thinking about the distribution of all temperatures observed at a given site, and then say maybe looking at the 99th percentile or the top 1% of those temperatures. This will be the definition that Nels will be using in his talk, and he'll talk quite a bit more in depth about how we can think about probabilities in extreme heat. So why do we care about extreme heat? The first reason we care about extreme heat is human health. Very high temperatures and extreme heat can impact human health, can cause heat-related illnesses like heat stroke, dehydration, and often these heat stroke and dehydration can exacerbate pre-existing medical conditions. Also, in thinking about human health, it's important to think about the fact that extreme heat can be felt disproportionately both across the landscape and between different groups of people. And also that extreme heat can have compounding impacts with other natural hazards. A great example of this is in the summer of 2021, some cities like Denver and Salt Lake City had very high temperatures co-occurring with relatively high levels of air pollution from wildfire smoke and ozone. We also care about extreme heat because it impacts ecosystem health and creates a natural hazard for humans to deal with. When thinking about plants, animals, and fish, there are often thresholds of heat that these organisms simply cannot tolerate or cannot tolerate for very long. Good example of that are cold water fish. Once river temperatures get above a certain level, those water temperatures can create a lot of stress on those animals. And an example of a response to that can be closing a fishery, say on the upper Colorado River when water temperatures exceed 70 degrees. Also, extreme heat is part of things that cause drought, and drought can lead to wildfire. So extreme heat is kind of a compounding factor in both wildfire and drought. And more specifically, when fires start, there's often specific weather conditions that create extreme fire weather. And typically extreme fire weather includes very, very high temperatures, low humidities, and high wind speeds. And finally, extreme heat can impact our infrastructure, our human-built infrastructure. Very high temperatures can impact roads, bridges, and buildings. Those high temperatures can cause those building materials to expand and in some cases crack. Very high temperatures can also have an impact on water quality. That raises the temperature of water, which can impact levels of algal growth and particularly harmful algal blooms. So I first want to explore extreme heat in our region by talking about the all-time high temperatures that have been observed in our three-state region. And I'm going to be talking about Colorado, Wyoming, and Utah. In Colorado, the all-time high is 115 degrees observed at John Martin Dam just outside Lamar, Colorado in 1983. In Utah, the all-time high temperature is 117 degrees observed in St. George. And that's been observed several times, I believe at least 3 times, once last year and also just this past June. And in Wyoming, the all-time high temperature is also 115 degrees in Basin, Wyoming, observed in the 1980s. And I want to point out that the all-time high temperatures for all 3 states are very similar. However, when we look at other aspects of extreme heat, there are some stark differences between the states. Now, just to give a little better idea of some of the extreme high temperatures that have been observed in the major cities of this 3-state region. In Colorado, extreme high temperatures range from 109 degrees in Pueblo to 105 in Denver, 102 in Cortez, 107 in Grand Junction, and 103 degrees in Fort Collins. In Utah, we see slightly higher all-time temperatures. In Salt Lake City, 107 degrees has been observed at least 3 times, both in 2021 and 2022. 107 degrees was also observed in Duchesne in the Uinta Basin, 102 in Logan, 110 out in the West Desert in Delta, and 114 degrees in Moab. As we move more north into Wyoming, despite that all-time high temperature being very similar to Colorado and Utah, the all-time high temperature other cities in Wyoming are lower. 101 degrees in Jackson, 99 in Evanston, 104 in both Riverton and Casper, and 100 degrees in Cheyenne. So another definition of extreme heat can be using a temperature threshold and how many times that temperature threshold has been observed in a given year. So here I'm going to show the all-time records for the most 100-degree days in a given year for the 3-state region. In Colorado, in Denver, the most 100-degree days observed in a year is 6, in Lamar 43, and in Grand Junction 22. Now, here's where we start to see some larger differences between the states. When we move west to Utah, there's many locations in Utah that it's much more common to see 100-degree days. Just this year in Salt Lake City, there were 24 100-degree days. In Moab, the record is 58, and in Zion National Park, just outside St. George, the record is 79. And then as we move north into Wyoming, generally there's fewer 100-degree days observed. In Basin, the record is 22 for a given year. In Riverton, 5, and in Casper, 8 days. So third definition of extreme heat is thinking about heat waves. So not just the number of days that exceed a certain threshold, but when we see those 100-degree days on consecutive days. So here I'm going to show all-time records for the greatest number, the longest stretch of days where temperatures were greater than 100 degrees. And for Denver, Colorado, that's 5 days. Lamar, Colorado, 21 days. And Grand Junction, 12 days. Again, when we move west into Utah, we see that heat waves are much more common and often much longer. The record in Salt Lake City is 10 days, a 10-day stretch of 100-degree days. In St. George, 54 days, and in Moab, 38 days. Again, no further north in Wyoming, these heat waves are less common and often shorter. The longest heat wave of 100 degrees in Basin was 12 days, in Riverton, 4 days, and in Casper, 3 days. And one thing I didn't mention as I began this sequence of slides, in parentheses, is showing the year in which that temperature record was observed. And one thing I want to point out is that, especially in Colorado and Utah, a lot of these temperature records were observed in the last 20 to 30 years. In Wyoming, that's not quite so much the case. There are a lot of temperature records that still stand from around the middle of the 20th century or even the early 20th century. So kind of a final temperature threshold I want to explore is thinking about hot nights. So nights when the minimum temperature is 75 degrees or warmer. And while this doesn't quantify extreme heat in the way that we often think about it, we think about extreme heat as those just really blistering hot days. These 75-degree nights are important when thinking about human health, especially for those humans who are not in air-conditioned spaces. Having multiple long stretches of nights where it's just not cooling off doesn't allow the human body to recover from the impacts of heat. And especially when there's other health considerations for individuals, this can really cause a significant stress on the human body. Generally in Colorado, there's not very many warm, really hot nights. Denver has not observed a 75-degree minimum temperature night. In Lamar, the record is 5 days during a summer where nighttime temperatures were 75 or warmer, and 2 days in Grand Junction observed just last year. However, in Utah, these hot nights are much more common. In Salt Lake City, just this year, there was a record number of nights during summer where temperatures were 75 degrees or warmer, with 24. In Moab, that record, and in St. George, 21. And I want to point out the difference that we're seeing here. When we're looking at extreme high temperatures, we're seeing more 100-degree days, higher temperatures in places like Moab and St. George. But in this case, in Salt Lake City, we're seeing more of these hot nights. And I'll go into that a little bit further in a future slide. And then in Wyoming, similar to Colorado, we don't see very many nights that are warmer than 75 degrees. So now I want to start to think about, now that I've given a little historical context of sort of what the boundaries are of extreme heat in our region, I want to think about how temperature and extreme heat has been changing over the last 100 years or so. So this graph and the next few graphs are showing temperatures in Salt Lake City, Utah. This is a pretty common graph that many of us might be familiar seeing, that mean annual temperatures across many locations in the West have been increasing, especially since 1970 or so. And in fact, if you look at the first 30 years of this temperature record compare it to the last 30 years, there's been a 2.5 degree temperature increase in Salt Lake City, considering mean annual temperature. However, we're really interested here in thinking about these extreme temperatures. And typically the warmest month is July. And this graph here shows the mean maximum July temperature since 1929 in Salt Lake City. And this has also increased, but by a little bit more modest of an amount compared to mean annual temperature. The mean annual, or the mean July maximum temperature has increased only by about 2 degrees Fahrenheit in Salt Lake City. However, when we look at nighttime temperatures, we're seeing a much more pronounced trend in an increase in the average July minimum temperature since about 1970, 1980. And in fact, comparing the first 30 years of the record to the last 30 years, there's been nearly a 6 degree temperature increase in the mean minimum July temperature. So this is a huge change, and one that's really been accelerating over the last couple of years, especially in Salt Lake City. So I want to take, now with thinking about that, we're seeing a climate change impact on temperatures. We're seeing it in mean annual temperatures. We're seeing it to some degree in July maximum temperatures, and very much in nighttime temperatures. I want to explore a little bit how climate change might be impacting extreme temperatures. So, and I'm using a definition of extreme temperatures of all-time record highs. So for this little analysis, I looked at sites that had temperature data for at least 100 years in Colorado, Utah, and Wyoming. And then I looked at this across time. So how many sites how many sites have all-time records from different 20-year blocks of time, from 1890 moving to 2022. This graph here looks at Wyoming in that way. And we can see that, so on the y-axis, you have the number of sites where an all-time temperature record was broken. X-axis, you have these different 20-year time bins. And in Wyoming, there were more all-time temperature records that have been set since the late 20th century, since about 1951. I do want to point out that this last bin is not 20 years. It's 2011 through 2022. When we look at Utah, there's much more pronounced of a trend of seeing more all-time records that have been set in the last 20 to 30 years. And then when we look at Colorado, we still also see that trend. It's not quite as heavily distributed to the last 30 years, but since about 1970 is where the majority of all-time records in the state of Colorado were set. So now I want to just briefly go back to some of the trends that we are seeing in Salt Lake City. These very high minimum temperatures, the fact that the record for the greatest number of nights where temperatures exceeded 75 degrees, we actually saw the highest number of those in Salt Lake City compared to St. George or Moab. And this has a lot to do with the urban heat island effect. So what I mean by this is that urban areas often are hotter than rural areas. And this is because the built environment in urban areas is comprised of lots of dark surfaces like asphalt, concrete, buildings, shingles on the top of buildings that absorb radiation, and they keep that radiation longer and overall lead to higher temperature increases than we see in more rural areas, and especially during nighttime temperatures. So to look at this, I'm going to compare Salt Lake City, which is in an urban area. I do want to point out that this temperature data is from the airport, not the core of Salt Lake City. That said, there's an awful lot of dark surfaces around the airport as well. And compare this to a rural area, Tooele, in the next valley over. These are at similar elevations, similar latitudes. So in theory, we should see similar temperature changes. However, when we briefly look at mean annual temperatures, Tooele mean annual temperatures are on the left, Salt Lake City mean annual temperatures on the right. And we can see that there's a greater temperature increase in Salt Lake City of about 2.5 degrees compared to about 1 degree in Tooele. However, this urban heat island effect is really much more pronounced when looking at nighttime temperatures. So these two graphs look at mean July minimum temperatures. And in Tooele, you see a similar increase to mean annual temperatures, just over 1 degree Fahrenheit increase, comparing the first 30 years to the last 30 years. But then when we move to Salt Lake City, we're seeing that 6-degree temperature increase in July minimum temperatures. And a large part of the difference between these two sites, this urban heat island effect. Tooele is a much, much more rural location. Salt Lake City has grown rapidly and grown tremendously from 1928 to 2022. So very briefly, this is just slightly out of place in this talk, but it's relevant because a lot of the information that I have taken and presented in this talk came from information that is presented on the Utah Hazard Planning dashboard. So just this week, Western Water Assessment launched a new information dashboard, the Utah Hazard Planning dashboard. This particular tool, it's modeled after the Intermountain West Climate Dashboard and provides information about hazards and hazard planning specifically for hazard planners in Utah. And it presents information on this list of hazards here, which are the whole array of hazards that are planned for in Utah and are pretty much the same in Colorado and Wyoming. While this information is specific to Utah, I want to stress that many of the resources presented in this tool are relevant to all 3 states and elsewhere in the West. And just finally, to introduce Nels's talk, I want to briefly give context for some of the extreme heat events that Nels will be talking about. The summer of 2021 was an extremely hot summer for the Western United States. This graph here this map here shows statewide average temperature ranks for summer 2021. So these states that are in red with a 127 on it, those are the hottest summers on record in June through August 2021. And this was the time period that was really dominated. Some of these high temperatures were really driven by this heat dome event that occurred centered over the Pacific Northwest in June. This heat dome, while not as intense further to the east, it also impacted Utah, Western Colorado, and Western Wyoming. And now I'll pass this to Nels, and he will talk a little more closely about these events.
Thanks, Seth. Let me get my screen up here. Does look good, Seth? All right. Yeah, so I'm going to give kind of an introduction into some of the heat projections for the Western US from a number of different reports, and do a little bit of exploration of an analysis that we did on these 2020 events that Seth alluded to. So to start things off, there are a number of ways in which we project changes in extreme heat. This figures from the 4th National Climate Assessment for the Western US. What we're showing here are the number of hot days, that just the straight up number of hot days in each summer projected by mid-century in the Western US, and kind of these are days above 90 degrees Fahrenheit. So this is one way we can think about projected changes. This recent report by the First Street Foundation, one of the ways that they project changes in increased heat are increased number of local hot days. So akin to kind of this like heat wave idea of number of days over a threshold. And they demonstrate by mid-century, you get a much higher probability of achieving 3 consecutive local hot days than we see in the kind of modern climate. And then more of the way that I'm going to be discussing extreme heat events is we can think about the probability of very large heat events across the Western US. So this is a figure from the Intergovernmental Panel on Climate Change, the 6th assessment report that came out last year. And we can look at the increase of probability of what we call a 50-year event. So this is an event that is likely to only occur once every 50 years in the pre-industrial period, as we're kind of classifying it. Now, in the future, and I mean, even in the present, we have already seen an increase in the likelihood of this magnitude event. So in the present, they report that this, what was once a 1 in 50-year event, is maybe now a 1 in 10-year event. So it occurs 5 times probabilistically in this 50-year period. And then globally at 2 degrees warming, extreme heat events that occur probabilistically once every 50 years occur about once every 3.5 years. So about 14 times in a 50-year period. So when we're thinking about, these projections, one of the questions we want to ask is climate change increasing the likelihood of record-breaking events? So are we going to continue to see these really extreme hot events like we've seen in the last couple of years? And before I get to answering or approaching those questions, I want to talk about how we think about the probability of these events and how that probability changes. So if we take, here is a sample distribution of data that I've generated that is about the magnitude of what we experience here in the Intermountain West. You can look at the entire distribution of maximum daily temperatures for a summer. And what we're really interested in is this kind of upper region of the distribution, where the area under this curve is the probability of the most extreme temperatures. And if we zoom in, we can get an idea. Here I'm using a 95-degree threshold. You can get an idea of how probabilistic exceeding this temperature will be for, let's say, this station where this data might come from. Now, what impact does climate change have on the probability of extremes above this threshold? Well, one way we can think about it is a shift in the entire distribution. So a mean shift towards higher temperatures, you kind of move your distribution over, and then you zoom in again to the upper regions, and you say, in this case, it looks like we can eyeball about maybe doubling of the area underneath the red curve, which is our new warmer temperature world compared to the black curve here. And so the meaning of this is essentially it would lead, this warming that we induce in this example would lead to a doubling of the probability of these events. So this kind of gets a schematic view of what an increase in global mean temperatures does to our probabilistic understanding of extreme heat. But in reality, not all temperatures are so normal, and this is kind of thinking statistical terms normal. So here are examples of distributions of maximum daily summertime temperatures from Portland and Salt Lake City. So for the Portland International Airport, we have what we call a positively skewed distribution. This implies that we have much larger tails above the mean and the possibility for very large temperature anomalies. So a bit of foreshadowing here, if you were to experience a 116-degree day, that's going to be really shocking in Portland, because most of your normal life temperatures lie somewhere in here in your maximum temperatures. But you extend way out here, and that really is a shocking experience. Now, in Salt Lake City, we have inner Mountain West region, we have more negatively skewed distributions. And now these have shorter positive tails with potentially less surprise or risk for extreme surprise temperatures. So if you were to experience a 116-degree day in Salt Lake City, you would probably think, wow, it was a very hot day, but you might not be so shocked as you would if you were, say, someone living in Portland. And now we can look at quickly at the tails of these distributions just to kind of further understand what we're talking about. When we look and zoom in on the tails of these distributions here using a 100-degree threshold, the difference between the positive and negative skewed distribution really becomes quite apparent, where in the positively skewed distributions of Portland, you can see that the probability of really reaching far beyond these thresholds is small, but it certainly exists. And we need to consider that when we're thinking about how probability of these extreme temperatures change. Whereas in Salt Lake, you have more of a truncated distribution. You can still get quite warm temperatures, but you don't nearly reach as far out into this kind of shocking part of the distribution as you do maybe in Portland. So if we look at the map of the distributions of, or the skewness of the distributions of maximum daily temperatures, they're often not normal. In fact, here is a map of the US, again, using Portland as an example on the top panel, and Albuquerque, which is my home city. I'm biased towards it. In the kind of bottom example, you can see that along the West Coast and up in the Pacific Northwest, you have more of these positively skewed regions, more vulnerable potentially to extreme surprise temperature excursions. And in the Intermountain West, you have more negatively skewed regions, so more truncated tails, but still there is a possibility for extreme heat, as Seth has shown has already started to occur and is projected to continue occurring. But the question we ask on this is, what effect does this have on our understanding of the probability of extreme heat events, kind of even in the current climate? So if we point to the event in Portland, this was kind of the newsworthy event that happened in 2021. We can use this as an example to evaluate how statistics and physical mechanisms can inform or not our possibility of an extreme heat event. So showing the extreme heat event, the couple of days that fall far outside the bulk of the distribution of daily temperatures from all years leading up to the event, many standard deviations outside of it. You get this 116-degree day, and then you get all these news articles where folks are quite surprised, and reasonably so. And many of the kind of orientation of these articles was towards this impact of climate change, really speeding up the likelihood of these extremes. But a question that I had was, has climate change induced a sudden change in the probability of extremes, or is there something about the way we're estimating the probability that really informs what we think is probable or possible in terms of extreme heat events? So what we did is we did a couple tests of different methodologies that you might use to estimate the probability of extreme. And one way that you can estimate these probabilities is to take your annual maximum temperature for every year leading up to the event. So this is all data up to right before the 2021 event, and use what's often called a block maxima approach, or annual values, in a generalized extreme value theorem distribution. And so we did that. We took all of the data from Portland and we fit this distribution. And unfortunately, this methodology says this event is not even possible. And now that might be a little bit baffling, because we know that it was possible. So clearly there's something slightly flawed in this approach that doesn't inform us of what we might expect in terms of extreme heat. So another way that we might approach this problem is take all temperatures above a certain threshold, say the 90th percentile for a season. This is often called a generalized Pareto distribution. We fit all of that data to this kind of extreme value distribution, and all of a sudden the event looks like it is possible using this alternate method. And I just want to use this as an example of how really carefully considering the statistical approaches that you apply can help to inform what is not only possible, but also potentially very probable within the framework of planning for public health or infrastructure, or for a number of purposes. But predicting the probability or possibility of these events does not need to only be statistical in nature. As Seth had pointed out in his presentation, we have these kind of heat dome events that are associated with high atmospheric height anomalies, and they are very commonly driving these extreme heat waves, heat events in the Pacific Northwest, but also in the Intermountain West. And I'm using some figures from these two manuscripts by Bumbaco et al. And Thomas et al. To demonstrate that these atmospheric events often are very much related to the most extreme temperature events that we observe in the West. And so we applied a approach that takes some of this data and some of the data of the atmospheric height anomalies to the 2021 heat wave. And we want to see, could we have seen the heat wave coming, using a more kind of mechanistic approach to understanding the probability of the event. So this is a figure that has quite a lot of information, but I'm going to go through it and kind of orient you to what we are showing here. We're relating geopotential heights, so these atmospheric height anomalies, to daily maximum temperatures. And in the top right corner, this is the Pacific Northwest heat wave. And when you look at the bulk of the distribution, you might fit a kind of linear relationship. There are a couple different periods here, but it doesn't change all that much between the two time periods. You might say, well, this relationship doesn't explain what's going on in the extreme part of the distribution. We wouldn't really expect to see temperatures that large when we are using this kind of general relationship fit. But we're really interested in the most extreme heat events. So we want to predict what extreme temperatures are possible for given geopotential heights and use that to inform what we might need to plan for or might need to plan for experiencing in the future. And so the approach that we take is we do what is equivalent to kind of a quantile regression approach, where we take the maximum possible temperatures that are observed for bins of geopotential heights and fit a kind of linear relationship to those values. And by using this approach, we can demonstrate that, our new prediction line, two of the points fall kind of quite nicely within this fit. One of them is even more extreme than we could predict with this line, but this gives us a sense of the temperatures that we might need to plan for and that are certainly possible. And both of these results, the kind of statistical approach or testing that we did and this kind of evaluation of the physical relationships, lead us to the conclusion that we need to adopt strategies for predicting heat events, because we need to be able to predict not only that something of this magnitude is possible, but also that it is more probable than we might have previously thought. And that's really quite important in terms of planning. And so with that, I'll just end with a couple points on some of the challenges in terms of extreme heat and future projections. We have short records, really, and even 70, 80 years, those records are short compared to the rarity of these extreme events. And so it necessarily implies that there's going to be some uncertainty in our estimations of extremes. Now, climate models can help to some degree, and so can flexible statistical tools, but we kind of need to do more work to address this challenge in extreme heat probability prediction. Changing statistics other than just like the mean shift that I showed the schematic of can occur. So changes potentially in those skewness values. And that can alter the utility of statistical frameworks for future projection and prediction. And as Seth mentioned, there are also feedbacks within the climate where drier soils, droughts can kind of exacerbate the impacts of extreme heat events. And so more work needs to be done on those relationships as well. But things we can start planning for now. It is going to get warmer, and this is a kind of an obvious point, but mean shifts lead to increases in the probability of extreme temperatures and the magnitude of the highest temperatures that we experience. And we've already seen that occurring. As Seth pointed out, nighttime temperatures are projected to increase much more than maximum daily temperatures. So we should probably plan on less resilience of cool nights. And a point here is potentially we need to kind of understand how cool nighttimes need to be to alleviate from extreme daytime temperatures from a public health perspective, so we can better understand how we can plan for our most vulnerable populations. And kind of continuous with that point, not everyone will have the resources to effectively alleviate themselves from extreme heat. So we need to plan on allocating resources to help those who are not able to effectively alleviate themselves. And with that, I will turn things over to Katie, who will be exploring some of the impacts and implications of extreme heat for communities and managers with a lens to equity issues.
Great, thanks, Nels. Okay, give me just 1 second here. Nope. Thank you, Seth. Okay, great. So I'm going to be, Nels and Seth did a great job talking about the climate side of extreme heat. And for this last portion, I'm going to dig into some of the societal impacts. This is a huge, it's a huge topic, so I'm not going to hit them all, but I'm especially going to focus a little bit on who is at risk and some strategies to respond and offer some resources for folks who are interested in this. And I guess to start out with this, I mean, Seth gave us a larger background around this, but planning for extreme heat, as we're seeing, we've had those types of experiences in the past, but this idea of planning for it and developing plans at the state and community level are largely new in our region, especially for Colorado, as higher elevations have offered those nighttime reprieves from this type of risk. But conversations with stakeholders indicate this is one of the most pressing impacts, particularly for vulnerable communities, and one that our region has had less experience managing. So Seth already touched on this a little bit, but one of the main reasons we care from a social perspective or human perspective about extreme heat is its impact on health. Heat is the #1 weather-related killer in the US, and temperatures extreme directly affect the health by compromising the body's ability to regulate its internal temperature, and this can cause a number of heat illness, heat cramps, heat exhaustion, heat stroke, and even fatalities. And it also exacerbates pre-existing conditions, things like asthma, heart disease, diabetes, can lead to preterm births. So it has a number of different health impacts. And from a biophysical standpoint, children, pregnant women, and older adults are more susceptible to these types of extreme temperatures because they are less able to regulate their body temperatures. However, for reasons I'm going to get into later, other groups are also at high risk, including those who work outdoors, those who might be more socially isolated, low-income communities, or people of color. And it's important to note that this health risk can be both derived from extreme heat, right, these really high temperatures, but also prolonged exposure to heat that might be slightly less high temperatures. So before I dig in, I think it's important for us to think about what we mean when we're talking about heat risk. So risk, generally, we understand as a combination of probability and consequence. Nels did a great job digging into the probability, but on the consequence, there's 2 key factors I think about when thinking about the human side. So first is exposure, and this is a measure of the physical hazard. So in this case, heat, right? How hot it is. Or, you know, thinking about flooding, another hazard, it might be living within the floodplain makes you more exposed to flooding than, say, you know, someone who lives on a hill at a higher elevation. It says nothing about your capacity to respond to those events. So the second factor is vulnerability, and these are the characteristics that make an individual or a community more susceptible to harm. You can imagine 2 neighbors have really different vulnerability, but maybe the same exposure. And this would be due to things like resources, access to transportation, insurance, social networks, a number of factors. And this helps explain why we see such differences in risk and impact. So this leads to really different spatial distribution of risk. Seth already talked about the urban heat island, comparing, you know, urban areas to rural areas, but actually if we go at a much finer scale, we can still see really dramatically different exposures to heat. Here we, you know, on the other side, we see Phoenix, Arizona, and you can see just its neighborhood to neighborhood differences. And this can be because of the same urbanizing principles that Seth talked about. Access to shade, pavement, concrete leads to these really hot areas within an urban area. But because within cities, if we look at that scale, between 2 neighborhoods that might be just miles apart, we can see differences in experienced temperature up to 20 degrees Fahrenheit between different neighborhoods within the same city. And these differences often and repeatedly fall along both racial and economic lines. So it's worth taking a moment to dig in a little further. So researchers have recently been producing a number of striking findings about the impacts of racist housing policies, particularly redlining, on extreme heat exposure. So for those of you who aren't familiar with this, redlining was a practice of categorizing entire neighborhoods to determine the level of risk for mortgage lending and insurance. These categories were based in large part on the racial makeup and of these neighborhoods, and minority neighborhoods were marked in red, hence redlining, and considered undesirable and high risk for lenders. And this happened across the country and led to decades of disinvestment in these areas, furthered racial segregation between neighborhoods, and significantly contributed to the racial wealth gap. We can see on the left here's Charlotte, North Carolina, and you can see the red, those are the redlined areas, and then the green is the most desirable or lowest risk. And researchers have found that these areas that were historically redlined have significantly higher temperatures for their counterparts. So it's explaining some of this difference within cities. So for example, Portland, Oregon, here on the right, the formerly redlined areas, which are blown up or darkened, I guess, were on average 12 degrees warmer than the green line neighborhoods, the ones categorized in green. And this is true across cities. With a study of more than 100 cities, they found that 94% of formerly redlined areas were at minimum 5 degrees hotter. And Denver ranked second, only to Portland, with a difference between these, again, the green lined areas that were rated most desirable, being a spread of almost 12. So we can see these numbers are from an average. So these green areas, the neighborhoods that were historically green lined, are almost 7.5 degrees cooler than the average temperature in the city, versus the redlined areas are almost 5 degrees warmer in the same city. And this is, of course, is true in our region. Actually, in our region, there were only 4 cities that were redlined, in part because we just, had less urban development, in part because of the racial makeup of our area. But the 4 cities in our region were Salt Lake City, Ogden, Denver, and Pueblo. So here's Denver. We can see some really significant differences in temperature across this. And this is looking at the longest day of the year in 2017. But so longest day of the year, June 21st. So another area that's a spatially explicit area that has very high heat risk and high exposure are mobile home parks. Mobile home parks are the largest unsubsidized source of affordable housing, with more than 2.7 million residents in this country. So, they have high heat risk both because of physical exposure as well as being socially vulnerable. And a unique feature about mobile homes is typically the home itself is owned by an individual, but the land underneath is owned by a landlord, which complicates your ability to do some of these take some of these preventative measures to reduce heat. So recent research found that in Phoenix, Arizona, for example, in Maricopa County, where Phoenix is located, less than 5% of residents live in mobile home parks. But in recent heat waves, 27.5% of the deaths were found, indoor heat-related deaths were found in mobile home parks. So a striking and deeply unsettling statistic. Some reasons for this are the built structure. These are less insulated and often less sealed. Landscaping and shade, those are often decisions landlords make that not individuals can make about trees. Most or many lack air conditioning, and those who have it often struggle to afford to pay for air conditioning. By definition, these areas are largely low income. They also have high elderly populations that live on fixed incomes. And in regions like ours, they often have high populations of minorities, like Latinx populations. So both formerly redlined areas and mobile home parks are both places we can look at exposures, but for the reasons we discussed, also have high levels of vulnerable populations. And there's other ones beyond that that I'm going to just quickly cover. We already discussed elderly and children. The unhoused is a particularly difficult population to protect because they don't often have access to cool temperatures. Outdoor workers, those who might be in agriculture or warehouses and deliveries, that's another population. The poor or energy burdened who cannot afford to cool their house, even if they have access to air conditioning, and people of color. And this is just a quick map to show, or a quick graph to show, while the West has seen a significant increase in the amount of homes with air conditioning, like a higher increase than others, we still, at least 2015, have much lower levels of homes that have access to AC. So this is an issue of communities, of people being able to cool themselves within their own homes. So responding to heat quickly, I'm going to wrap up with this. Responding to heat, there's two sides of this. There's both heat mitigation. This is more on preventing heat, reducing heat, and then heat management, what you do to support people being resilient during heat. So in terms of heat mitigation, trying to prevent heat, cooling cities and neighborhoods, we have elements of urban design, shade structures, both either built or through canopy and trees. We have green roofs and green walls. This can cool by reducing heat reflection. And transportation, this can include both cooling pavements as well as reducing parking lots and roads and supporting alternative forms of transportation. The next is heat management. And this is not trying to reduce the amount of heat there is, but supporting people being able to cope with heat. And these are two examples of education for folks on how to change their behaviors to support resilience during heat. This is a major undertaking by public health officials of how do we help people make individual choices that support safety during heat times. So this can include staying hydrated, staying indoors or in shade. A big issue is people leaving children or animals in cars, not realizing how hot those get, cooling down, finding ways to find water, etc., and checking in on vulnerable community members or people who are isolated and don't have a lot of mobility. And then there's some work that needs to be done at the community level that's beyond the individual level, particularly for vulnerable populations. And this can include cooling centers for communities, as well as policies that protect folks, like outdoor workers in California now have legislative rights for water, rest, and shade. So I'm going to conclude now. These are resources that I think Vinay will put in the chat, and I will stop now.
Thanks, Katie and Nels. And we have just a couple minutes left in the webinar. I don't see any questions in the Q&A right now, but if anyone has any questions they'd like answered in the final few minutes here, please feel free to type those in. Or I believe there's also a raise your hand function, and you can just ask your question. We can hang around here for just a moment to see if there are any questions.
Yeah, Seth, I also wanted to, while we wait for potential questions, point to a resource, heat.gov is a website that launched not too long ago that has a number of resources related to heat events, heat planning, and vulnerability. And I can link that in the chat as well.
Okay, thanks, Nels. Here's one question. This is for Nels. What does the atmospheric physics say about the possible maximum?
Yeah, so this is a question that we are kind of currently working on at my research group at the University of Colorado Boulder. Currently, there is not a really comprehensive mapping, let's say, of what the maximum possible temperatures are and their relationship, particularly with these atmospheric events that drive these heat domes. But that is something that I think we really want to investigate more. It's worth developing kind of this comprehensive data set so that folks can plan for what is possible. But this really, the work that that I demonstrated in my talk leads us to that question. So we're kind of thinking on the same wavelength, you and I. There's still some uncertainty on that, but we would like to constrain that more.
Thanks, Nels. Here's a question potentially for Katie. Did you look at adaptation resilience measures that do not raise greenhouse gas emissions?
Great. Yeah, thanks, Juan. I mean, that's a really important question because then you can get into elements where adaptation might be maladaptive if it's only increasing the hazard that you're worried about. So that's a really important element. I mean, a lot of adaptation measures that are, moving from parking lots and mostly vehicle transportation to biking and those others, that would be reducing greenhouse gas. Keeping more urban greening efforts, I think, also fall under that. But it's a really important consideration for thinking about how to move forward in a just way, in a way that sets you up for continued success rather than perpetuates the issue.
I would also say one other resilience and adaptation measure that is actually good in terms of greenhouse gas emissions is green infrastructure, planting trees, things like that for shading. However, that also can be potentially an issue that you need to think about maladaptation depending upon what your water availability is. So some of these hottest places are also places that are running short on water or need to conserve water. So these are value judgments that don't necessarily have easy question or easy answers.
One other thing I'll say is that I know in mobile home parks in Boulder, one of them, they've invested in solar power for those communities. So that would be, example of how do we both increase air conditioning access, which we know has greenhouse gas emissions, but also, find a way so that that's not increasing greenhouse gas emissions.
I think we have time for just this last question. I think this is towards you again, Katie. Even though heat can impact certain communities more, do some of these same communities have better social networks, such as local friends and family, that check on elderly compared to a well-off elderly person that may live alone in a nicer neighborhood?
Yeah, that's a fantastic question. There's actually a really kind of a famous study of the heat wave in Chicago, and I think in 1995, where they looked at death rates and found and explored why did we see one low-income Black community have the highest rates, one wealthy white community have like middle level, and then one other low-income Black community have the least, and said, why did we see that pattern? And these social connections were the answer. So the low-income Black community that had very few deaths was because it had been a long-standing community where there were a lot of social ties and community members connected. The low-income Black community that had a lot of deaths was one that had been resettled and had a lot of, the neighborhood had had a lot of gentrification. People didn't know each other as well, and there were less social ties, and that had led to less community members connecting with people, checking in on people. And I think, the white wealthier community was in the middle. So I think that piece of social ties is really important, particularly for people with disabilities, lack of mobility, elderly communities. That's a great question.
Great. Well, I'd like to thank everyone for joining us for this webinar. If anyone has any questions that come up after this webinar, please feel free to reach out to Western Water Assessment. You can find our contact information on our website. And thank you again for joining us.